So thus far, when we've been talking about magnetic fields, we've mostly concentrated on this one here. Magnetic field strength, or flux density, which has the units Tesla and the symbol B for magnetic field strength. So we've talked about that in the past, and we talked about how that's related to how squashed together the lines are. If the magnetic field is strong, the lines will be squashed together a lot. If the magnetic field's weak, they'll be spread further apart. This year we need to update our understanding by talking about flux itself. Flux has the symbol here, and its units are Webers. So flux is just basically talking about there being a magnetic field in the area, and it's determined by how strongly or how dense the field lines are, how strong the magnetic field is, and the area that we're concerned about, the area that the field moves through. So as you can see, if we had a strong magnet and these field lines were squished closer together, we would have more magnetic flux present. If we were concerned with a larger area, we would have more magnetic flux present. And the reason why this is useful, the chief reason why this is useful, is it generates Faraday's law for us. And Faraday's law is at the heart of magnetic induction. There's a complicated mathematical derivation for this, which I'm not going to go into today. If you are interested in the derivation of Faraday's law, we can go through that in class. But what I'm chiefly interested in is these here, the idea of flux and how it changes gives us our understanding of induced voltage. So any voltage that we get is equal to the change in the flux divided by how quickly the flux changes. So I hope you can see this is a rate of change issue. How big the voltage we get depends on, and the minus sign is there to show that we're always getting a voltage opposing the change in flux. So obviously, if we had a very, very strong magnetic field, because the flux depends on the strength of the magnetic field, we would get a big voltage. If we changed it quickly, we would get a different voltage, how fast it's changing. If it changes quickly, it'll be a larger voltage compared to if it changes slowly. So when we look at things like generators, where you're taking a coil and spinning it in a magnetic field, what you're actually doing is you're getting a voltage because you're forcing the flux inside that coil to change quickly. As you spin the handle, or as the wind turns the turbine, or the water turns the turbine, you're forcing the flux to change. The coil is literally cutting across, as it turns, cutting across the flux lines. And that's causing a change of magnetic field inside the coil, and that's what gives us our voltage. So Faraday's law is at the heart of electricity generation, and we're going to be looking in particular at a specific property of or application of Faraday's law in inductors.